is around 15 milliseconds. So it's very, very fast. It can go from very sticky addition to just detachment and again sticky again. I mean, you want to stick to the interface, but you want to run out when you have to. So you need a means to regulate interfacial addition. And this is where we are still a bit far away from a technological perspective. And of course, I mean, being able to regulate addition in a so fast manner would be very good for, I mean, soft manipulator, optics, grippers, soft robotics in general, robot-human interaction. So this is the background of our research, where we see applications, basically. But yeah, let's go to the central question. What is vibration? Well, it's a very recent topic. I would say last time I talked here in 2024, there was only this paper out, only the first one. So yeah, those are mostly from my group in Bari, and yeah, this is from a group in France instead. And you can see they are all very, very recent. I mean, the first evidence was in 2020, was by this paper published in Nature Communication, where basically they did indentation. Just imagine classical JKR indentation, but this time this silicon material is kind of shaped. And it's shaped at a certain frequency and with a certain amplitude. And I mean, typical numbers would be like 300 Hertz, 400 Hertz, so below 1 kilohertz or around 1 kilohertz, and amplitude in the order of tens of microns. And what they show was that when you do so, the pull-off of this classical JKR contact could be changed by even one order of magnitude or even more. So it would be extremely, you will have an extremely important effect on addition, which may be reducing it, or it may be also enhancing it. So you can destroy addition, but you can also enhance it by one order of magnitude, even more. So for vibration, we will say, I mean, from now on, is a technique to regulate interfacial van der Waals addition by means of high frequency, low amplitude vibration, okay? Yeah, we can talk about what does it mean, low amplitude and high frequency, but maybe, yeah, we will have time later. So let us, this is the setup we have. I want to start with the experimental result. So the evidence, basically. So those are two electrodynamic shakers. You have here a PMMA beam, and on this, you have a PDMS sample that's sitting on the top. So while we do the classical indentation, I mean, this is a lens, a borosilicate lens, like 52 millimeters in terms of radius of contact. So we brought it in contact and then we unload it. Of course, while we do so, we measure acceleration, we measure forces, we measure indentation, and so on. But the thing is that while you do this indentation test, these electrodynamic shakers are guided so that they provide some vibration at the frequency and amplitude that are desired. Yeah, this is a video. So here vibration is off, and here also off, but then you can see that now it will be on, and see the contact area is almost doubling. I mean, the contact radius is almost doubling, forces remain almost the same, and then you are unloading, and I mean, in this particular case, this is no vibration curve, detached at around 400 millinewton, while here we are at 1.5 Newton, so it's at least 4 times larger. Maybe we can show it again. So loading is the same for everyone, then dwell time, we wait the contact to settle. Then look here, when vibrations are on, you see it's just get very larger contact area, and then you will just have unloading. This is same setup, but this particular case is for a 20 to 1 mixing ratio of PDMS, thickness is 5 millimeters, contact radius is 50 millimeter, 51, frequency 300 Hz, amplitude of vibration 60 microns, and 500 micron per second. That's yeah, unloading velocity. So dwell time, well, we use it to settle the contact. This is, of course, a viscoelastic material. Then vibration are on. We wait a little bit for the contact to settle, so that we can start all the, let's say, transient process have just ended, and then we are just unloading. You can see that when we start vibration, forces are basically not changing. This is a load-controlled experiment, but we do have a quite soft rubber band that on which the indenter is hanged. So this actually will behave as mostly a load-controlled setup. Well, what are we looking at? Well, we have a soft material, and so, of course, we have to include viscoelasticity there. And viscoelastic material, this is just the standard linear solid, just to, keep some idea in mind. A low and high frequency is like behaving like an elastic solid, but in the transition region, this will dissipate a lot of energy. And when you have a crack that is propagating at the interface of a viscoelastic solid, you need to take into account also the dissipation, the internal dissipation of the material. So basically, this is the concept of Persson and Brenner. You can use cohesive model by Chapery, by Greenwood, but I mean, in general, what you must have in mind is that basically you are putting in some energy into the system, and this you need it to create new surfaces. So classical fracture mechanics concept, you need to create new surfaces, but also you need to compensate the power that is dissipated within the material due to viscoelasticity. So this leads to kind of an enhanced work of addition that we can measure macroscopically and include these two contributions. Of course, in an elastic problem, you wouldn't have this power dissipated in the material. And then we thought about a lumped model that could describe this problem. So we are exciting this interface. So this is like this rigid sphere acts like an indenter, is like an oscillator. It is hanged at with a certain stiffness. So we can control the movement of this point. This is the substrate we are talking about. And what we did, we just write the equation of equilibrium for the spherical indenter, where, of course, we have to include the contact force. And this will be a nonlinear problem because now the contact force is nonlinear. We choose the JKR contact model because we are looking at soft materials. But clearly, we need to include also, in a certain manner, the effect of viscoelastic dissipation. And this was done by rewriting the JKR contact model with a certain effective surface energy. The effective surface energy is because of what I explained. We need to take into account also the viscoelastic dissipation within the material. And this has been shown that can be fitted very, very well by a Gente-Schulz approach, which means that if this is the crack velocity, you can see that the apparent surface energy would scale as a power law, will generally scale as a power law. This is well testified on several. This is, of course, an empirical law, but is well accepted and well documented in many papers. You can see here one from Creton, actually, on 10 orders of magnitude, basically. So we use this Gente-Schulz empirical law to implement this into our model. So where the dissipation is coming from, because the opening and the closing of the crack are two very different processes. So if you have a crack that is excited with a cyclic load and it's opening and closing, this opening and closing is not following the same trajectory. It will follow a different trajectory, and so you will have hysteresis, and this hysteresis will be basically the origin, what will give you internal dissipation. Then you can write, of course, all the model in a dimensionless form to be integrated. This we just integrated by with a numerical screen. We did it in MATLAB. So this is basically the Gente-Schulz law that will enter into the contact model and will enter within the dynamic equilibrium of our system. Input parameter is, of course, this x of b, which is basically the excitation we are providing with certain amplitude and frequency. So by now it's just harmonic excitation. So you can see here some results from the numerical scheme. So you see this is a classical JKR curve. So you stay here, you stay in equilibrium, and once you apply vibration, you have this jumping contact area that you can see also here. So you just start vibration and you have a very big jumping contact area, which is, if you remember correctly, is what I showed in the video. As soon as you start the vibration, you have this very big jump in contact area, and then you start unloading up to a certain pull of force that by now is like this 20, while this JKR would be just 1.5. So you have enhanced addition by factor 10 or 15. And of course, you can create a map. You can create a map because this pool of force will change with respect to the amplitude of vibration, with respect to the frequency of excitation. And of course, your system will show a certain resonance where this effect will be amplified. And so we can see kind of two of this point, like 2 and 4. 2 is close to the resonance. What is happening here? Here you are exciting the system, you are exciting close to a resonance of the system, so the oscillator starts to oscillate very much, and this oscillation will cause the crack tip going back and forth, so it will cause a lot of dissipation. And that's why you get very large amplification. This is going to be around 30. If you take instead 0.4, then what you see is that basically you are exciting far away from the resonant frequency. So basically the indentation will be given by the amplitude of the vibration you are imposing at your substrate. And of course, in this case, amplification is a bit smaller than with, what happened with well, close to the resonance. So what we did, now we have the model, now we have the experiment. What we did, we conduct several indentation experiments without vibration. So no vibration at all. We just want to characterize the interface in terms of this Gent-Schulz behavior. So which means in terms of dissipation, how dissipation will change as a function of the velocity. So we make different unloading, different indentation tests, different unloading rate. Then you put everything, all those points using basically the JKR model on this curve, and you can fit a certain Gent-Schulz law. This is going to be like 0.5, which the exponent, which is very classical for this type of soft materials. And then, having characterized the behavior, the dissipative behavior, adhesive and viscoelastic behavior of the interface in this way, we go ahead and we try to now compare with experiments. So what you see here is the green curve, the gray curve here is just the quasi-static case. Then you are just sitting here in equilibrium, and then you start vibration. In this case, we are simulating 300 Hz and different amplitude from 20 to 100 micron. And you can see all the dots. Those are the experimental result. On the contrary, the solid line is the theoretical result. Well, it's a fairly good agreement, considering that it's just a lumped model, so it's very easy to implement and solve it. But this is not just good if you look, at macroscopic for like just the pull of force. You can also look at this in terms of time. So this is the force, basically. We are unloading it. So again, experiments, and solid line is the theory. I mean, it is the model. And also here, this is the contact radius. So solid line is the model, and the stars is the experiments. You can see that that is, I mean, a fairly good agreement in between the model and the experiments. I mean, we basically don't have here any fitting parameters. I mean, we are just putting there the mass of the indenter, the elasticity, the stiffness, and the damping, and the Gent-Schulz law that we have characterized previously in quasi-static conditions. So no fitting parameters here. This is the experimental pull of force, and this is the numerical one. Of course, it would be good if they would be on this line. They are on this line up to 800 millinewton. Consider the JKR contact case would give 60 millinewton as a pull of force. So here we are enhancing the pull off by factor 14. Okay, and then you have saturation, and this saturation is, I mean, we explain it because of some instability at the interface. So when vibrations are too large, you have this instability that you can observe that leads basically to detachment. So I skip on this secondary fact because I think I'm running out of time. So we have developed a lumped model for vibration. We have compared this with numerical experiments and with the experimental results, and we think this is kind of a good model that predicts fairly well what is happening here. Yeah, thanks very much for the kind attention. Special thanks to the people that have collaborated on this. And we are organizing a colloquium in June 2027 in Bari. So you're welcome if you want to come. Thank you.
Perfectly into it. We have time for questions. Yes, I'm just asking about your model. I mean, you had this term, the damping term, C times X dot.
Yeah.
Isn't the viscoelastic model already damping enough? And then the question is how do you choose these parameters?
Yeah, good. Yeah, of course. That's a good point. So we try to keep it separated, like what is viscoelasticity in the Gent-Schulz problem and the characterization of the interface, and what is like internal damping of the system, like the spray, the oscillator, and so on. So what we did, we just did some free vibration analysis of the indenter, so without any contact, so just in plain air, you just detach it. I mean, this is easy because, I mean, you get in contact, you have adhesion, so you just keep on going and you have pull off, and then your interface, your indenter will start just to oscillate. And from the decay, we just take the damping. So this would be the damping in the oscillator, not related to the interface.
Nice talk. So as I understand, it jumps up in the contact area when you switch on the vibration. It jumps up to a bigger value. Now, if you switch it off again before pull off, does it go back to the same value or some other value?
Absolutely, it goes back. It goes back. Yeah, I mean, we have not done, a systematic analysis if it's going back exactly where it was supposed to be before. So, I mean, I cannot just, be 100% sure. But what I can tell you is that if you're just unloading and you are in certain condition, and then you just switch off vibration, you just get a full detachment immediately. Okay, and or if you are just in the middle and switch it off and then switch it on again, then it will jump again. So it looks very reversible in a sense. Okay, you do that, you switch off, and then it goes back again. Yeah.
It's a very interesting problem. Can you go back to Gecko at the end? So why is it so efficient for Gecko? What happens that it can run fast?
Oh, well, that's a different story in a sense that what links this problem to the Gecko is the time scale. As you have like 300-400 Hertz in terms of vibration, then you can say switch on and off vibrations like in 100th of a second or even less. So this means you have time scales in terms of addition regulation that is comparable with the Gecko. Then how the Gecko does it, it's completely different. No vibration there. Is of course has a brain, has nerves and muscle, and can tune the orientation of all the seta and spatulae to get the right condition. But if you want to do this in a robot, it means having like 1 million of termination or billion of them to control. This is what Gecko from evolution has been doing. So the idea is we want to achieve the same performance in terms of switching time scale, because then you can run. But the way we do that is completely different from the Gecko.
I have a last one. So, the follow-up, the control you can switch on and off almost immediately. But does it affect also the contact area on the same time scale, or is this slow?
No, it's not affecting it exactly at the same time scale. And maybe if I go back to the video, yeah, you can see that. I mean, vibrations are really sharp, activated when the dashed line will appear, while you can see that the time scale for the contact area is a bit longer. It takes few seconds, let's say. It's still very fast, but it will take, let's say, few seconds, while here we are at 300 Hertz, so vibrations are there already very, very fast.
So let's thank the speaker again. I will speak about physical origin of friction relaxation and interrupted slide. Please.
So hello everyone, my name is Baptiste Boulet. I'm a PhD student under the supervision of David Almas and Julien Schebert in the Laboratory of Tribology and System Dynamics in Lyon in France. And so today I will speak about the physical origin of friction relaxation after interrupted sliding, which is part of my thesis, funded via a project of the French Research National Agency. So to define the so-called right-hand side law, one of the two main experiments is the slide of slide one. During this one, we are usually observing the dependency of the friction, of the static friction coefficient to the holding time after a continuous slide. On curves of those experiments, the holding time is easily discernible thanks to the to the quick drop of the friction coefficient from the dynamic one to below it before stabilization. But this drop does not seem us to be explained, even if it's consistently observed. So today, we will try to explain the physical origin of the friction relaxation and try to find if it comes from bulk or can also come from an interfacial reaction. So we propose to realize model experiments on between a smooth PDMS field on the glass plate. And for a fixed driving speed, we defined a shearing distance of 100% as the one necessary to obtain the static friction coefficient. From this, we define multiple shearing distances where we stop the interfacial shearing to observe the tangential force relaxation over time. We can divide our system into two parts, a bulk one and an interface one on the interface. Since our bulk is made of an elastomer, viscoelasticity is obviously expected to come from it. So we're now trying to answer the question if the tangential force relaxation can come only for the bulk or also can from a time-dependent reaction of the interface. And to do so, we need a trick to dissociate the bulk viscoelasticity from any potential time-dependent reaction of the interface. And to do so, we propose to bond the sample with its contact surface. So we'll make the same experiments in a standard way with samples sliding freely and in a stuck way with samples stuck to the contact surface. So the apparatus used for those experiments was previously conceived in the laboratory. It's enabled to capture in operando real contact images while handling precise displacements along 3 orthogonal axes and accurately measuring forces and displacements along them. Our samples are made of Silgard 184 polydimethylsiloxane mixed with a curing agent to base ratio of 1:10. They are molded in a smooth optical lens which have a curvature radius of 9.42 millimeters, and they display a Young's modulus around 2.5 MPa. Since we want to observe global as well as local contact behaviors through images in the lens and before molding the bulk, we lay a layer of PDMS sealed with particles after a first layer of pure PDMS. The first layer of pure PDMS is here to keep full PDMS and glass contact and avoid any any contact particles interactions. Sorry. We estimated the particles to be located between 50 and 100 micrometers in the sample. And for the bonded experiments, to deny any slip of the contact, we use a plasma cleaner. This device activates sample and contact glass surfaces on few nanometers and allows us to strongly bond them under our selected normal load without modifying the bulk compartment. The experimental protocol is made of 4 steps: a normal loading to 1 Newton made in 5 seconds, a 600 seconds waiting time to get free of the large majority of viscoelastic effects of the normal load, ensuring also that the sample is systematically in an equivalent stress state and correctly bounded in the latter case. Then the shearing is applied with a speed of 0.1 millimeters per second on the calculated distance. And finally, we're waiting 5 minutes while maintaining the normal load as well as the shearing position to track forces on contact aspect evolution. Experiments being done, we draw the curves of each shear level for unbounded and bounded cases. First, for the 125%, we will discard the curve because the sample failed during the test due to a crack that initiate and propagate in the bulk itself. We can note that the tangential force reached at stop in both protocols are way different, which is consequence of the existence of partial slip in the unbounded case. Let's now focus on the evolution over time of the tangential forces relaxed after stop. We can observe two very different behavior. For the unbounded case, we observe that the total relaxed tangential force grow quickly for shearing distances less than 90% and then stabilize. On the other hand, for the bounded case, the relaxed tangential force also rise, but its increase is way less important. To better compare those two cases, we plot tangential force lost versus time for 10, 50, and 100%. We observe that for 10%, the tangential force relaxation of unbounded and bounded systems are very close, whereas they deviate for higher shearing distances. Since the bounded process was here to deny any interfacial time-dependent reaction, we think that the tangential force relaxed in the bounded case is only due to bulk relaxation, while for the unbounded case, it is made of both bulk and interfacial contributions. By plotting the total relaxation force as function of either the shearing distance of the tangential force at stop, either the shearing distance or the tangential force at stop, we can observe that the bulk contribution may remain almost constant, while the total contribution, and thus the interfacial one, progressively increase. At 100%, the interfacial contribution in the unbounded case is nearly 4 times larger than the bulk contribution. So from all of this, we can conclude that tangential force relaxation originates from both bulk and interface. Now, to try to elucidate the origin of the interfacial relaxation, we will study the slipping state of the interface both during initial shear loading and during waiting time. Indeed, an important phenomenon that arises at a slipping interface is the presence of partial slip, well described by the Cataneo-Midlin model. Since partial slip is heterogeneous, we will next try to determine if or not the interfacial slip state during relaxation presents a similar spatial distribution. So thanks to the particles buried in the sample, we can use digital image correlation to observe displacements and deformation fields in and around the contact. These fields are close to the ones predicted by the iterator, namely a displacement close to the imposed one far from the contact with reducing values approaching it. Partial slip can even be observed with a reduction of the stuck zone in the contact center. To make reading of those fields easier, we propose here to track 7 points of the contact fields, globally aligned with the contact center and sliding direction. DIC measured displacements are here plotted against global tangential forces. The main part of the curve is the shearing process, and the agglomeration of points at their end correspond to the displacement measured during the 5 minutes waiting time. Those curves allow us to observe similarities and differences between in and out contact points. First, for low shearing percentages, here it's 25%, points of the contact stay in place while the tangential force relax. Secondly, points outside the contacts also seem to stay in place while the tangential force relax, and this seems to stay true even for higher shearing distance percentages, here 25%, 125%. However, at such percentage, points inside the contact continue their movement during relaxation in the same direction as the one before the stop. This last point seems to be the signature of the interfacial tangential force relaxation occurring via slippage. So to better catch this behavior, we observe it not on only on the 7 subsets, but along all the central line, where this representation show high correlation errors being mainly located on contact edges. So we can attribute them to heavy brightness variation from out to inside the contact between 2 images. To mitigate this issue, we modified the images by fading the contact. We modified the images to fade the contact. First, we precisely detecting it, and then increased the pixel brightness inside the contact up to its edges. So we obtain smooth curve. With rerunning the digital image correlation, we obtain smooth curves and can plot their weighting parts separately. So here are the evolution of the displacement during waiting time as a function of the tangential force. Since all those curves seem at least monotonic, we perform linear fit that allow us to extract the mean displacement per relaxed force unit in each shearing percentage. The contact is here represented by opaque part of each line, where its outside is in symmetry aspect. So the contact in the center and outside in symmetry. Since no displacement is measured in the bonding case on the right, any displacement observed in the unbounded one must necessarily correspond to an interfacial slippage. So focusing on this case, we can now clearly observe what happens during the holding part of our experiment. First, outside the contact, we can observe a displacement that vanishes as we are going far away from the contact edges. Second, for low shearing distance percentages, the central part of the contact does not move after stop, while an increasing proportion of it coming from edges is moving. This may recall us of the Catano-Midlin partial slip and can suggest that only parts of the contact who already slipped during shear can move after the stop. But third, we can observe that all the contact is moving during the relaxation for a shearing distance percentage of only 75%. And in this case, full slip is not expected to be reached. Indeed, if we plot the DIC mutual tangential speed just before the stop on the right, we can see that at 75%, a stuck part is still present in the middle of the contact. Moreover, we can observe that in all cases, the proportion of the contact moving during the wait is higher than at the end of the shear. So to keep the Catano-Midlin common representation, we can say that the slipping ring of the relaxation is thicker than the one encountered during the shearing process, and so can totally supplant the central stuck zone. So even if the direct correspondence between the spatial distribution on the slipping zone during relaxation and the partial slip is not perfect, there is still similarities between them and this will require further investigations. So let me sum up what we saw today. First, the tangential force relaxation originates clearly from bulk and interface. In addition, the interfacial relaxation becomes more predominant over the bulk one as shearing distance percentages and tangential forces rise. Then, despite the reduction in tangential force and consequently of the shear stress at the interface, a movement can be observed in the same direction than during the shearing. Finally, interfacial relaxation is signed by an expanded sliding ring compared to the one of the cathode milling partial slip, being able to totally supplant its stuck central zone. Oops, sorry. So thank you for your attention.
Few questions.
Yes.
Just one question on it. Maybe I didn't understand this correctly. How does the surface roughness influence your observer?
We're working with smooth surface where the where the control surface is a microscopic glass slide. We expect it to be smooth enough, and the sample is made in an optically smooth lens, so it's quite smooth. But I'm okay with the fact that it's not perfectly smooth, but we did not observe the roughness of the
Any further questions? No. So let's thank the speaker again. Next speaker is from the University. We'll speak about shifted penalty multi-grid method for contact. Please.
Is it okay? Okay. So, good morning, everyone. I'm Gabriele Marchi, PhD student at Università Italiana here in Lugano. And today I'm going to present our shifted penalty multi-grid method for contact. I will start with the motivation or the goal. The idea is that we want to perform simulation involving real geometries. That means that we want to be capable of capture even the small details in the geometry we want to simulate. You can see here some example where this aspect is crucial. This is an optic nerve where there are these internal bodies and there is self-contact, or maybe a more general example is tire design, where you want to, there is a rough surface and then there are all the details on the tire, and you want to be able to model this kind of details. And so the goal is to perform simulation and particularly high performance, high resolution simulation. And in this direction, new opportunities came from new hardware. We had the opportunity to collaborate with the CSCS Alp supercomputing system that is here in Lugano. But obviously, having even a very powerful machine is not enough to get this goal. It is crucial to develop and to design algorithms that are designed and tailored for this kind of architecture. And some good example of this aspect we can see here, like this exascale computing project where they use high-order finite elements to improve locality and matrix-free operators, and also some very good examples from the computer graphics community where they have this idea of exploit the hardware. And overall, our goal is to be in the context of fluid structure contact interaction. That means that we are on, our setup involves a fluid and an elastic body immersed into it, and we have this kind of dynamics, and also the elastic body gets in contact with the boundaries of the domain or even with another elastic bodies. And so it introduced some additional difficulties because we have physics constraints due to the multiple physics, and often we have over-constrained problem because we have the fluid that pushes against the boundary, and then we have this contact constraint. And so we need a solver that is scalable, as we said before, but it's also very flexible. And our what we are going to propose here to this problem is our shifted penalty multi-root method that is based on an augmented Lagrangian formulation of the contact problem. And this problem is solved in a multi-level multi-root method, and everything here is designed for a matrix-free implementation, and everything I will show you is relative to a single performance device. This is the standard formulation of contact, so it's several times this morning. We have the equation of elasticity and then standard Hirth-Signorini contact conditions. So we have non-penetration, adhesion, the complementary, and at this stage we focus on frictionless contact. So we can see this problem actually as a minimization problem, the elasticity term, subject to this inequality, the non-penetration one. And since, as we said, we want a flexible solver, probably the most flexible and simple one is the external penalty method, where we solve our minimization problem subject to this inequality, but obviously it requires an infinite value of the penalty parameter. So we move to the augmented Lagrangian formulation. That is a family of methods that is well known and used in the constraint optimization in this kind of problems. And in particular, we use the shifted penalty method. And the idea is quite simple. You can see an example here. We have our unconstrained problem that is at the end the elasticity. And when we want, and we're looking for a minima, obviously, because we said we can consider it as a minimization problem. But we want this minima, our solution, to be into the feasible region, meaning the region where no penetration. And so we can introduce the shift that actually moves the minima towards the feasible region. Obviously, there is a drawback, that is that we introduce a new unknown. So now we are solving for the displacement and also for this Lagrange multiplier or shift. And it turns out that we have this min-max problem where we have this strain energy for the elasticity, and then we have this additional term. Without this term here, just simple penalty, we penalize the penetration, but then we introduce this term here, and in this way we have a theoretical satisfaction of the constraint, even with a finite penalty parameter. We solve this problem in an iterative way, so we fix lambda and we solve only the minimization problem for u, and then we update lambda once u is computed according to the Zawa update rule. So we say we want to solve our minimization problem. Probably the simplest way is to using standard Newton methods. So here you can see the gradient and the Hessian. The green terms are the one related to the elasticity, while the orange ones are the two related to the contact. So now we have this system we want to solve. Actually, we reduce our problem to solving this system, then update lambda, and so on till convergence. And we want to solve this system. And as I said, the goal is to go to a high resolution. So you can imagine this system composed by a huge number of unknowns. So obviously, the direct solver is not feasible. So the idea is to use an iterative solver. But as you probably know, iterative solvers are very effective in reducing high frequency error, but they struggle in low frequency ones. So we consider a geometric multi-grid method. The idea it's quite simple. Instead of working only on the fine grid, we consider a hierarchy of grids, and we solve the problem at each level, going from the finest to the coarse and back through a V cycle. And yeah, the main idea is that an error or a signal that is has a low frequency here, when restricted to the coarse one, result to be a high frequency, and so it can reduce very quickly to the same smoother. And this is an example of why multi-grid methods is very effective. It's just convergence rate only for 2D linear elasticity without introducing contact. Just even a quite small example, but here on with the orange and blue lines, you can see the convergence rate is the evolution of the residual for standard methods, and here you can see the efficiency of the multi-grid cycle. So the idea is, okay, we formulate our problem in our augmented Lagrangian formulation. Is it a question?
The horizontal line.
Yeah.
What is that?
This is, okay, this is at each iteration, the the actual residual divided by the initial residual. If our linear elasticity problem, this is just a system, the linear system solved with Jacobi, the blue one, and Gauss-Seidel, the orange, yellow one.
So the Gauss-Seidel and Jacobi are on top of each other.
Yeah, that means that they're very slow. Okay, yeah. So we formulate.
You just solve the linear system with
Yeah.
Jacobi and
Yeah, this is just an example of why using this multi-grid cycle is a good idea. I mean, at least for a very simple problem. And so we say, okay, we formulate our problem with the augmented Lagrangian formulation. We want to solve it with this method. And the only remaining part is how to embed the nonlinear term related to contact into this multi-level framework. And this is an idea of the method. You can look at this version here. This is a simplified version. Here, this is the Newton loop, where here inside lambda is fixed. So here we have the standard linear multi-grid cycle. And we introduce this nonlinear pre-smoothing and post-smoothing. And the idea is that we perform some iteration, updating the contact-related term, so the degree the action related to the contact, and then we perform some linear smoothing on the entire operator, so including also the elasticity. And even here, everything is designed for matrix free, as so hold the operator accords to this idea. And then here there is this beta parameter that is a line search parameter on the correction. So when going from the coarse grid to the finest, we have this line search parameter. We can discuss later the efficiency. So we iterate here until the residual is small enough. Then we update lambda. This is the Husserl update rule. We update lambda through a gradient Hassen step that is then projected to the feasible region. And then we iterate until convergence. We test our solver starting with very, very simple examples. This is just Poisson problem or elasticity 2D with planar contacts, spherical contacts to validate the solver. And we compared our results with the monotone multigrid. You can see here the displacement deviation in L2 norm. This is the Poisson problem and his hard elasticity. And in red, the number of iterations required by the monotone multigrid, and in green, the iteration required by our solver. And you can see that, especially for the case involving elasticity, we had an average of 30% less iteration and an accuracy up to tolerance in all the cases. This is a more detailed analysis of the convergence rates. Here we're plotting the norm of the penetration and the norm of the gradient. The plot on the left is for the Poisson case. We have 0.15, that means a reduction of about 85% of the quantities at each iteration, while here for the elasticity, 75%. Then we test the robustness of our solver against increasing complexity in terms of geometrical complexity and stiffness of the problem. As you can see, the solver result to be quite robust against the indentation level, but obviously the number of iterations increased with the Young modulus. But we proved that at least for linear elasticity, we can rescale the entire problem by the Young modulus, so we can reduce to the best case for each value of the Young modulus. But this holds only for linear elasticity. And then another key property of multi-grid-based method is mesh-independent convergence rate. That means that the number of iterations does not grow with the number of degrees of freedom, and we prove this property. And then, as I said, there is the effect of this line search. At this stage, we developed only a linear line search based on a linear term. The goal is to include the entire energy to develop even a more effective line search. But you can see even here, the light ones are the number of iterations required without line search, while the darkest one we did, and you can see that even at this stage is quite effective. And then we move to some, we say, more complex problem, even if it is still quite simple. We have this elastic cylinder that models an aortic root, and inside we have this obstacle that models a stent. And we have this initial situation with hundreds of penetration points, both on these nodes here, but even in the connecting branches. And we perform this simulation. This is the results. And this is a simulation involving 500 million degrees of freedom on a single GPU, so single device. And obviously, it was feasible only through our matrix-free representation. And you can see here the a zoom in of the resolution. This is probably this point here. And you can see that thanks to this very high resolution, we were able to capture in a very detailed way the stress distribution. Yeah, this simulation was done, as I said, on this Grace Hopper GPU. Then we test even on different hardwares. And these are the experiments we use to test the performance. They are still quite simple, but 3D, contact against a sphere or multisphere. Still static problem. We use block-Jacobi smoother. And for the other experiment, we use Chebyshev. They are both compatible with matrix-free implementation. We use conjugate gradient with block-Jacobi as a coarse solver. And this is the number of iteration. You can see for each, different colors represent different level of depth of our multigrid methods, while we have a dotted line that represents the non-linearized problem, meaning that we re-linearize the problem at each iteration, we recompute the normals at each iteration, while the continuous line result to be, let's say, linear problem, meaning that we linearize only once at the beginning. So we use this kind of normals for the entire computation. And obviously for the multisphere, when we linearize several times, it requires more iteration. It's like solving a new problem at each iteration. While surprisingly, for the sphere, it requires even less iteration. And these are some time to solution. You can see here, for example, the biggest experiments, still the sphere and the multisphere, but a simulation involving 300 million degrees of freedom. And if you see it, the yellow one, that is the NVIDIA GPU, we were able to compute the simulation involving 300 million degrees of freedom, single device in less than 2 minutes. And here you can have more detailed insights of where we spend time during the computation. This, obviously, the main part is on the fine level, because it's where we have the higher resolution, but still also in the application of the block-Jacobi operator. So summing up, we present our shifted penalty multigrid method that is based on augmented Lagrangian formulation of the problem. This problem is solved through a hierarchical method, the geometric multigrid, and it supports matrix-free operator, so it allows to perform even, I would say, huge simulation on a single device, and it ensures accurate constraint satisfaction and optimal computational complexity, at least for let's say, simple experiment compared to the monotone multigrid. But obviously, this is just a work in progress. The idea is for sure to extend to dynamical contact and to friction. And then the goal is to include also multi-body contact and self-contact in order to get our complete setup in order to move to our FSI contact scenario. And in terms of performance, the goal is to develop an algebraic multigrid for the coarse solver, and at the end to embed the geometric and the algebraic multigrid through these hybrid methods. That's it.
Thanks for the presentation. We have time for questions.
You make some studies with different values of the block modules on the convergence. But what about studies on varying the penalty parameter? Like how does it?
I have it. I didn't put it into the slides because it's quite big. We submitted this work, so there is on arXiv the paper with all the plots, and we proved that even with very small obviously, increasing the penalty parameter requires less iteration, for sure. But we proved that at least on these experiments here, even with very low penalty parameter, like mu equal to 10 fixed for the entire computation, we were able to get the result. So I can show you later if you want. There, we have the.
And you gave an upper limit 10 to the power 5. What happens when you go over that? What breaks down?
Yeah, no, I mean, obviously the conditioning of the system getting worse. And at the end, this is the idea of using this augmented Lagrangian, not the penalty, that we can get, let's say, an accurate solution without the prerequisite of this big penalty parameter. So we can, we have an update rule for the penalty parameter here. Here we update the penalty parameter. It's quite small, I know. But if it still penetrates, we update the penalty parameters during the iteration. Sorry?
The penalty parameter in the iteration.
Yeah. But we tested even fixing the penalty parameter at the beginning. So let's set penalty parameter equals to 10, for example, and let it run without changing it. We get the exact solution. We converge due to the fact that we have this Lagrange multiplier that fulfills this constraint.
One more, if you allow. You have these graphs, horizontal, and which shows that Jacobian Gauss-Seidel is a very bad method. No, but is the culprit, so to say, the penalty? Is the penalty the reason why you don't?
No. This was just computed only on linear elasticity without contact. This is just an example. Okay, no contact here, just to show that why using Marchi could be a good idea. That's it.
Yeah, I mean, thank you very much. Very interesting. That's the update of the augmented parameter. I mean, you do it outside the Newton, right?
Yeah, exactly. Once the Newton is.
I mean, that's what I usually call augmented backgrounding. Then you get quadratic convergence for the whole thing. Whereas if you do it outside, only you are stuck with linear convergence for the total problem.
Okay.
Maybe I can add something. So it's not really actually outside the Newton loop. So we have so we have the V cycle, and we control how much reduction is in the residual, and based on that we have the mutation. But we don't have to convert linear to a linear solution. So in practice, we kind of achieve a sort of linear, the same cost of a linear solver with some small factor.
So much relation with the Newton.
So we have several linearization inside the smoother. So the penalty is linearized several times, pretty much per coordinate.
Yeah.
And then we have a V cycle, and after one V cycle, we see if we can update the shift or the shift or the condition.
Mm-hmm. Yeah, you're right.
Final question?
You had an example with over 500 million degrees of freedom.
Yeah.
Can you comment what the physical reason is why you need such a large number of DOI?
I mean, on this example, obviously, this is just a toy example. So, okay, just to prove that we can do it. And I mean, in this particular example, you probably get even quite similar results, even without a lower resolution. But when you move to more complex geometries, if you have like small bodies, small deformation here that has the same order of sides of the mesh, you need the same order of sides in order to capture. Because if you have this kind of resolution, you cannot represent objects that are smaller than the mesh size.
So maybe I can give two answers to this. Right, the first one is the scalability test. Because condition number explodes, and you would like to make sure that you're scalable and condition number stays bounded of the two-condition system. First one. The second one, from my point of view, what you rarely see in the literature is really boundary stresses. Right? People show deformations, but they rarely show boundary stresses. Now, how do you get the boundary stresses? Pointwise on a tetrahedral mesh, maybe. And usually they don't look very good. Right? If you look at boundary stresses, you see the quality of your solver and your discretization. I think that's why people usually don't show them. And so you need a high resolution on the boundary. You could do adaptivity and everything until you just did it in the volume. So I agree, for the biomechanics, you don't need this many unknowns, right? But for the boundary and for scalability, we wanted to know what was going on.
Okay, let's thank the speaker. Yes. Pozzolini from Lyon.
We will speak about application of the Nietzsche methods to pre-industrial 3D elastoplastic frictional contact problems.
Thank you. Okay. Hello, everyone. I'm Sir Pozzolini. I'm from Atom, and will present you a joint work with my colleague Maurice Pignol, Bruno Souloumiac, and Professor Yves Renard from INSA Lyon. Just to remember you that Framatome is the French manufacturer and the supplier of nuclear reactors and equipments. And in our work, we're facing to several contact problems, for example, for welding or cyclic loading simulation on crack elastoplastic pipes, thermo-elastoplastic contact problem. And in particular, in our steam generator, as you can see, there are several tubes, and all these tubes can be in contact. So, my presentation is about the Nietzsche method, and to present this method and the adaptation of this method for elastoplastic problem, I start to consider a domain omega composed by omega 1 and omega 2, and then to set my variable. I want to find u as a vector of u1 and u2, solving this elastic problem. And now I want to just to introduce the orthogonal projection from the master boundary to the slave one. And that's my contact condition, like my singularity condition. Just to recall you that this is my obstacle, and this is a frictionless contact problem. So, as you can see, you can reformulate the strong formulation as a weak formulation using a green formula. And my goal is to underline that this quantity can be replaced by this formula, and this formula is equivalent to my contact condition. And if I put this formula in this equation, I get the finite element method written in Nietzsche sense. In fact, in that case, I introduce a parameter, a real parameter theta, and we can get some different formulation of my Nietzsche method, symmetric one and non-symmetric one, very close to the penalty, and a screw symmetric. So now, as you understand how I can transform my weak formulation in a Nietzsche method for a frictionless contact problem, I introduce a Coulomb friction like this with my friction coefficient F. And as I wrote my contact condition using the Nietzsche formulation for the frictionless contact problem, now I rewrite the problem, the friction problem, using this operator. This is a projection on the ball center in 0 and this radius. So now I move to the elastoplastic constitutive law. So the stream is split into an elastic part and a plastic one. And then the problem can read like this. And I introduce my flow rules. Okay. That's classical. And I introduce my Hilbert spaces and a convex cone of admissible displacement. The elastoplastic problem can be reformulated using this kind of projector. And then the global problem read like this. I have to find U, the reaction, the normal reaction, the tangential one, and this is submitted to an elastoplastic elastoplastic law. Okay, in order to simplify the notation, I will denote by this operator the map corresponding to a pair of projection. The one represents the normal contact, and this one, the frictional one. So I get my niche contact term like this with my operator. So if I use a finite element method, that's my equation. That's the equation I obtain with the NIS method, with different parameter theta. So we implement this this algorithm in our software, Systus and Syswall, and from Atom softwares. And so the problem is a classical one for the contact. We need to evaluate the initial gap, perform a global search, a local search. We check the yield criterion. We compute the niche matrix and solve this problem using a Newton-Raphson loop. So this method had been tested on a deformable solid, and we do a kind of proof of concept that this more robust, and we try to test this method for large sliding. So I move to present you to some example using this niche method in our software. I start with spring compression. So for this study, we use Systus and the niche method with quadratic mesh for a better representation of the geometry and more accurate stress calculation. This is the isostresses as a function of crunching. And that's the maximal stress we obtain. And now we can visualize the contact pressure. And actually, we are working with my PhD student to introduce a numerical analysis of the plasticity law in this problem and the friction too. Now I would like to show you another example of tube expansion. This experiment is usually a cool forming process of a tube. This is my tube, and I put 4 rollers in my tube, and this is a plate. So what's the process? Mechanical tube expansion consists in plastically deforming a tube using 4 rotating rollers inside the tube, which gradually expand during rotation. So for this study, we use a quadratic mesh for better representation of the geometry and more accurate stress calculation with non-coincident mesh of contact surfaces. This mechanical expansion is well used in our steam generator with a lot of tube inside, as I said you. Why this mechanical problem is difficult? In fact, unilateral condition in the tube is done by the press against plate without penetration, signaling condition, and it's an evolving contact problem. And then we want to introduce elastoplasticity on both tube and plate. So we try to use our niche method in that context. So the problem is a roller in contact with a tube and a plate. Okay, that's our geometric constants. And that's the movie we obtain. In the first step, we can see the deformation of the tube before its contact with the plate. That's the von Mises iso stresses on this movie. That's one of the results we can obtain. And now I move to the second step, the deformation of the tube after its contact with the plate. And you can see the propagation of the deformation and von Mises iso stresses. We can conclude that we can get significant advantage using this niche method for this case with non-coincident mesh, deformable contacting body, and quadratic mesh for a good representation of the geometry. And we are still working on this problem to simulate spring back and compare our result with hydraulic expansion, which is much simpler model. And to finish, I would like to present you just another example. It's a clip experience. So in this problem, there is friction, just like this. And we can calculate the von Mises stress like this. So in conclusion, our niche method are more robust than our penalty method. This is variationally consistent. The conventions was proved by Franchuli and Yves Renard for the elastic problem. And this method doesn't need any additional degree of freedom. Then we have successfully applied this method for elastoplastic contact problem compared to our experiment results in finite deformation, in large deformation, and in dynamic with friction. But this method requires the 3D stress tensor to have realistic contact forces, and then obviously the problem arises for extension to tubes or 3D structures like plate or shell. That is why we started to work on this problem with contact problem for plate with one of previous PhD student. And now we are working with Mathieu Schorsch from Atom on the extension of the niche method for slender structures like tube, plate, or shell. Thank you.
One sentence caught my attention. You said have to be careful, non-symmetric. One line caught my attention. You said you have to be careful, non-symmetric.
Oh yeah.
So what was the origin of the non-symmetry?
Where is this sentence? Yes, the non-symmetric one is very close to the penalty, in fact.
Why when you have a symmetric? Well, the original problem is symmetric, and that's wonderful.
Okay.
Starting from spectral theory in Hilbert space to just symmetric makers. Why don't you use the symmetric method?
We introduced this parameter just to check the different formulation for the niche method, but perhaps Matthew or Yves can give an insight of this variation.
Just for complex models, the version C2 I guess you will more simple.
Sure. Yeah. It's a no.
Further questions? Time for one. I have one. As far as I know, Nietzsche's method, even in the symmetric formulation, can lead to indefinite systems. Do you encounter this issue here as well? So that depends on the problem setup and the parameters. Do you encounter issues with that here as well?
Not yet.
No further questions? Then thanks.
Thank you.
All the speakers can move on to the microphone.
Thank you. You can stop it now.
Charger.